Hello and welcome to the Filtration Breakout session. My name is Philipp Eichheimer and I'm leading the business area for filtration at Mastermarket, serving today as the host. Just to the beginning, I will go over some schedule so that you are prepared what will come in the next 1.5 hours. And then we'll slightly introduce my colleagues, Schabernack and Christopher Kühnle, who will give 2 live demonstrations. And then we'll start with a presentation on the news feature in GeoDict 2025, which is dedicated to adsorption. And then last but not least, we'll then directly give over to the presenters for the live demonstrations. Special, which is later for the roadmap. We will present the roadmap to all of the participants. And you may also give insights on what topics you would see on the roadmaps, which you like that we have on the roadmap, or which could maybe some interesting topics in the future which we can add to our roadmap. So this is later on some open discussions for questions and for input on our development map. Yeah, as already mentioned, so in the beginning, a quick introduction. Then I will give a presentation on the adsorption-based processes, then followed by the live demonstration, which deals with most of the adsorption is from Jonas. Then we'll have a small break depending on where we are in the schedule to get some refreshments, coffee, and then continue as we have here a switch then from media scale to element scale, where Christopher is showing then import and changing pleated structures in GeoDict, so the larger scale for simulation. And then, yeah, we'll conclude and give a brief outlook, which then includes also the roadmap and open discussions for further developments in the filtration business area. The first live demonstration will be presented by Jonas Schabernack from our support team. It will include very briefly the generation of packed bed structures, which are key to a lot of processes dealing with adsorption, from carbon capture or direct air capture applications, ranging to toluol and other chemicals which are harmful to the human and for engines. Then the generation of combined filter media. This is not specifically new in GeoDict, but we see as one of the latest or like the greatest features, which deals, for example, with combi media, which are very prominent in cabin air filtration applications, where, for example, include active carbon layers. And then last but not least, we'll give a short glimpse of how to set up an adsorption simulation. What are the input parameters? What do we get as a result? And how can we visualize it? The second live demonstration is given by Christopher Kühnle, one of my team members in the filtration. And he will focus on the larger scale, as we see here on the 2 pictures showing. So he will show how we can import CAD structures from filter elements or complete filtered with housing. He then will also showcase one of the features from last year, GeoDict 2024, where we implemented the generation of cylindrical pleat structures, where you can change the pleat count and pleat shape. And he will show here in combination that you can interchange the pleats, so you can delete the old pleats one and insert digitally a new one. And also show here how to set up a complete filter simulation and what can be the purpose out of that for your application. Just from our end, as we saw today in the presentations, there are large variety of new topics. Just briefly summarized one of the key features for especially the filtration industry, or like filtration simulation. Tomorrow we'll also see a presentation for our project, which is publicly funded, called ElexSim. This project is dedicated for 2 years and adds an add-in for FilterDict, and goals is here to tackle electrostatic forces, which have been already implemented in GeoDict, but we try to improve them and enhance them. So one point we are already dedicated on is we have a specific add-in for ElexSim, which now sum up all the electrostatic features. We implemented the electrostatic decay, so electrostatics also now become less and less when more particles are deposited on top of the structure. We implemented a dielectric phoretic force, and we enabled different modes of fiber charge. And to show here also that we have correct implementations and validations, we showed already that we can verify this with results for ANSYS. But yeah, known in GeoDict, instead of days, we simulate this in some minutes. Open points is still the validation we are working on, and then of course getting new insights from the electrostatics in general. Just a brief appetizer. There will be more tomorrow in the plenum presentations by Dr. Stefan Schumacher, one of the participants in this project. So what we see here, for example, are two materials which we are validated with measurements, which are highlighted here in gray, which are very good agreement. So this is just showing that we are working towards the validation between simulation and experiments to also give you a validated tool that is predicting the materials or like the parameters on your materials as you would see them in an experiment. The second new mention we have in the GeoDict 2025 is the support of a sub-voxel resolution. So the users which are already aware of the adaptive meshing in GeoDict know that the smallest unit we can have in a simulation is the voxel length itself. So we can coarsen in the far field, but we cannot go smaller than the voxel length. And this is now new in the LIA solver since 2025 on. So we can also in specific regions where we have, for example, global or local Reynolds numbers, we can refine and set sub-levels which are smaller than the voxel lengths, which then increases the precision in these kind of very narrow channels. For filtration, the application areas here would be narrow channels and filter cakes, so where we have very condensed material on top of filter media structures. And it also can allow better resolution for vortices, which we have in fast transient flows. This would be applications then for the filter element scale in future versions. So this is one of the technical pre-requirements towards the simulation of turbulence, which we try to tackle as we have more and more growing business in the complete filter or digital filter applications. And here we deal with high flow rates of air, oil, and these have a high tendency also to become turbulent at some conditions. One of the things I just want to also just small showcase here. So by GeoDict 2024, it was possible to have standard steady state flow, which we see here on the first two slides. And now what is possible in GeoDict 2025 is the simulation, for example, is here one famous common vortex street, which is, I think, well known in the engineering world. Details on that will be also tomorrow in the plenum session from Dr. Sven Linden. So he will give an entire talk regarding subvoxel resolution and improvements in the LIA solver. And last but not least, one feature which is, I think, not specifically to GeoDict 2025, but is that we, for example, can colorize the particles which we have in FilterDict, for example, by different parameters, for example. So first of all, we are able to analyze the depth of the particles and efficiency. So we can see if specific particles, how deep they reached into the filter media. We can colorize, for example, also the particles based on their deposition age. So we can see, for example, which particles have been deposited in the first batch, so in the very beginning, or at the end. So this gives sometimes nice conclusions to, for example, how the filter behaves over a lifetime. And these visualizations, which are particle-based, can be also for resonant times, number of bounces, or the status they are given in the FilterDict simulation. So if they are trapped or if they are just outbound. So these are things which are nicely to understand your feature and give more insights to your applications over lifetime simulations. Now I will move to the presentation of the newest feature we are having in GeoDict 2025 with the topic of simulation of adsorption-based processes to remove contaminants. So this is an additional feature on the Addict, and I will start with beginning and a bit of a technique. So how do we solve the adsorption? What are the assumptions we are taking, and which input parameters are needed? Then I will proceed with the validation. So we have two validations in this regard to showcase that the method is valid. And then I will give an outlook on possible applications, as well on the media and on the elemental side, which can give you ideas on how to use this feature in the future. As already mentioned in the beginning talk from Martina about the new features, adsorption is a crucial process in which filtration of gases, contaminants, vapors, or odors are used. And two important materials to mention here. So this is activated carbon and solides, which have the tendency to have large active surfaces inside of the structure, which are prominent to use in adsorption at the surface of these inner surfaces. The specific areas we are having is clearly water purification, where we have very small contaminants which need to be removed. Pharmaceutical applications, where specific pharmaceuticals need to be deposited on larger surfaces. Classical also cabin air filters in cars or in general in vehicles tend to have active carbon layers inside. Fertilizers in the agriculture are one of the specific areas to protect the farmers from the chemicals or pesticides. Heating, ventilation, so the HVAC and air purifier markets is also some markets you could use, and I think of a lot of processes which try to remove especially odors and vapors, for example. And last but not least, topics that have come up in the newest features regarding carbon capture and storage. So CCS, carbon capture and then utilization of these carbons which are extracted from the air, or direct air capture. So it can be directly at the source in industrial processes, or specifically for air fuels, also in the larger scope of industrial processes. The motivation and the challenge is that real-world experiments for adsorption can be, or mostly are, time-consuming. That's why in real world, we try to enhance the gas concentrations to obtain results in a faster time. But new applications, for example, require often very low gas concentrations, specifically in semiconductors, microchips industries, where really parts per billion are the units to work with. And here we need to gain more knowledge of the lifetime of filter. We can visualize it, we can analyze the flow, the diffusion, adsorption features to gain more insights and use these insights to optimize the filter. Using here breakthrough curves of the filter, we can improve the filter quality. We can save energy and resources by digital prototyping. So by using the digital workflow, we can save in prototypes, which can also save materials. We can optimize flow and residence times, so that also, for example, especially for active carbon or solides, the time for adsorption is ideally and all of the material is also adsorbed and used without losing the efficiency which is needed for the applications itself. In this sketch, I will show the adsorption process, how it's calculated in GeoDict. So as an input, we always calculate the flow around the structure. So we simulate the carrier gas flow. And one important parameter which we necessarily need is the diffusivity inside of the, for example, activated carbon or solides. For example, for the fluid, this is just literature value for diffusivity, but it's quite challenging to get this effective diffusivity for the adsorbents material itself. Can be done experimentally, which is quite tedious or expensive, but we offer also in GeoDict the opportunity with GeoDict to calculate this in GeoDict itself. After we have all its input parameters, we simulate the molecule movement of the particles and tracers. We track the tracer positions then and XY coordinates. And then we use the Langmuir and Torz adsorption isotherms, which are, I think, well known in this regard. I will come to that detail in the next slides, and solve this adsorption towards equilibrium, so that we see, okay, how much free spaces we are open and where are we at the adsorption isotherms, and how much of no places can be settled. We update then the adsorbed load in the structure depending on how much particle have been deposited on the finite number of deposition sites. And then we calculate, depending on if particles reach the outlet concentration. And this gives us a feedback then for the breakthrough curve, which is one of the results we are obtaining. And this simulates one batch for an adsorption simulation. And we can, of course, in GeoDict simulate several batches, which then increases, as we see in the last slides, the concentration at the outlet with increasing number of batches. On this slide, I will just briefly highlight the equations we are solving. So for the flow, we simulate Navier-Stokes-Brinkmann equations. As we always deal in the adsorption simulations with porous media, we always take into account the Brinkmann term. And for this, we also need effective parameters like the permeability and porosity, for example. The parameters for that is just purely obtained from the adsorbent directly and from the conditions of the flow. I don't want to get more into detail with that, but yeah, we can simply also just only solve the Stokes-Brinkmann equation, so the initial inertia term is dropped. This can be also done, depends on the application and the flow rate we are having in the gases. The adsorption isotherms we are using are Langmuir and Toth. So I think by most of you will be familiar with the most famous isotherm, the Langmuir, which considers just homogeneity of an adsorbent surface. We have a finite amount of adsorption size at the surface, and we can only adsorb one molecule or one tracer per adsorption site. This model is only valid for a monolayer, and we don't have interactions between adsorbates. So there's no interaction between the tracers during the simulation. We also took into account that we have, for example, the Toth adsorption isotherm, which is an extension of the Langmuir model. We see that it's a bit more complicated, so we need more coefficients from the laboratory experiments, but we also include temperature dependence. So this is the, we have then for different temperatures, different Toth adsorption isotherms. And this can be later also used, for example, when we have desorption, so that we have then different adsorption isotherms at different temperatures to simulate desorption again. In detail, what we assume, we have a monolayer, which we see here. We see it as in A, the adsorbent, for example, activated carbon or solides. At the phase B, the adsorbate may interact with the surface, and particles or like the molecules may be settled at these interfaces, but they can also, as we have an equilibrium, again, desorb, or like we have an equilibrium between particle or like tracers going to the adsorption site and also leaving the adsorption site. And this is done over batches. So these bind to the surface and there are no adsorption sites left. And then at the end, the concentration of the outlet increases. And molecules can also detach and switch back to the gas phase, depending on where we are at the adsorption isotherm's equilibrium state. For this, classical for GeoDict, we use our voxel-based method. So instead of solving here for the microstructure, we are using porous voxels. The amount of the adsorption sites is given by a maximum load, which is a Q with stars. We use tracers inside the porous zone, so they lose or gain concentration, while the porous voxel itself gains or loses then corresponding adsorptive load. So when, for example, a tracer enters the porous voxel and loses concentration, the porous voxel gains adsorptive load in this regard. The adsorption speed, like the dynamics of that, is determined by a gas concentration, a number of the free sites we're having. And the desorption speed is only determined by already occupied numbers we are having. And for this, classically, in most of the applications, a linear driving force model is used, which we're showing here. But additionally, if you want to, for example, separate the adsorptive and the desorptive velocities from each other, you can also choose between a dual driving force model, so that we have both kinetics, the adsorptive and the desorptive, can be separated from each other, which is in the linear driving force merged into one reaction constant. This gives then the opportunity to simulate adsorption in GeoDict. So what we're seeing here is we have a packed bed structure, and we see the adsorptive load going through the tube. The concentration at the outlet is increasing. So at the beginning of the simulation, everything is adsorbed, so we don't have any outlet concentration. And then we have the partial adsorption, where some of the parts are already full, so no active adsorption sites are open anymore. And at the end, where we have the no adsorption happening, is where all the material goes through, because there are no active sites open. What we see here very nicely is that we also can simulate or replicate boundary effects. where we have the effects between the grains and the porous particles. So what is optimization potential here is to say, okay, we have either different container or different particle sizes, because the flow is here in some places, especially at the rims, very dominant. And for example, to use this packed beds a bit more efficient, we could design different containers or use different sizes of the activated carbon, different mixtures to get the flow and the enough time for the adsorption itself. After explaining how we simulate the adsorption, I will just go to the next step, which is validation. So we have two validations present here. The first one is the CO2 injection on solids. So here we use the publication freely available in the internet, where we have pressed pellets of 2 millimeters diameter in the tube with given dimensions. And then we inject CO2. All the adsorption parameters we have from the publication, which is done experimentally, but also the paper uses comparison to COMSOL. And of course, what we are comparing to is the measurement of the breakthrough curve from Coker Knox in 2014. Some people who are interested where the parameters coming from. And we see by the plot we are showing here, so on the x-axis we have the time in minutes, and for the y-axis we have the relative outflow concentration. And we see that in red, GeoDict, and in blue, the experimental measurements of the breakthrough curve have an excellent agreement. In this simulations, we have the Torth adsorption curve used. The domain size, to get the numbers here, have been 350 times 350 times 2050 in the domain sizes, which sums up to 250 million computational cells. And in each batch, we used over 500,000 tracer cells, and the runtime has been 40 hours. So, and I think in this result, there have been around 20 batches. So you can imagine 500,000 batches times 20 batches times 500,000 tracers per batch in 40 hours are quite nice performance. The second validation uses activated carbon. And here we are using toluol injection, which is a classical standard test for automated cabin air filters. And here we have a different tube with different dimensions, and the pellets have been smaller, 1.3 millimeter diameter. And also publication was Carantala and Abril in 2009, where they measured the breakthrough curve. And what we also see here, that we have a very good agreement with the measurements. We see that especially at the beginning and the end, where the curves go to from the no adsorption and to the complete adsorption, fit very nicely with the simulation. In between, we have one measurement value, which is a bit off, but yeah, that is something to see also in experiments. The domain sizes here have been more or less similar to the previous validation. We have 320 times 320 times 1,250 voxels, which sums up to 128 million computational cells. And we used 390,000 batches, tracers per batch, which adds up to a runtime of 41 hours. So with validation, we showed that we have for two very famous systems, CO2 with solids and toluol with activated carbon, we can reproduce the experimental measurements with GeoDict very well, which gives you the confidence to use the feature in your applications. And now we'll go for the application itself, giving some ideas where you could use this adsorption feature in your application. One example I already mentioned at the beginning would be cabin air filters. So this is also some topic in the live demonstration, which follows soon, how to use them in GeoDict. So we see here activated carbon beds, which are set between two non-woven layers. And for example, here could also think of carried out particle and tracer filtration at the same time. That's also possible in GeoDict. What we see, for example, here is that also the adsorptive load, we are seeing that at the beginning, the particles come from the top to the inner. Things to optimize here would be like giving enough time for the adsorption to happen, increasing the surface area through smaller particle diameters, and for example, choose different materials to enhance the filter performance. This gives also the benefit to the suppliers, for example. Moving from the media side to larger scales, as we have also in GeoDict the capabilities of Pleat scales, we can, for example, use adsorption also on the filter scale. We see here in the video an adsorbed load on a pleat with multiple layers. So in GeoDict, it's capable up to 5 layers. And we see here that only the second layer has adsorption activated. And we see that nicely when the flow comes from the bottom and goes through the pleat, how, for example, adsorptive sites are tackled with the traces. The breakthrough curve we are given is also highlighted on the right-hand side. And for example, using this in combination with the pleat optimization would give feedbacks to, okay, for example, how many adsorptive load is necessary, and can we maybe, for example, make the layer thinner and have more pleats, for example, in the same surface area active for adsorption. The same when we have several pleated structures to represent larger domains. The same also implies to the second live demonstration of Christopher, when we, for example, can load CAD structures inside and then put cylindrical pleats with several layers into that, and yeah, simulate on entire filter cases, the adsorption and the flow. So this gives you 2 parameters. We have once the flow, which is anyways of key interest for the entire digital filters, but we can also simulate adsorption at the same time or in a coupled simulation. One topic to address is the desorption again. So this, for example, is the more or less reverse option for the adsorption. So here what we have, we can use already fully adsorbed structure, and we can simulate this desorption. For this, we load the structure, and then we can, for example, increase the temperature, which is then represented by a different equilibrium by either Langmuir or Toth, which is at a different temperature, which then features more the desorption of particles than the adsorption. And simulate then here the desorption process. So for example, what I show here is the adsorptive load. So at the beginning, we have the full adsorbed load of the structure, and over time, these desorption takes place, and adsorption sites become available. And the image here on the right-hand side represents the state after no desorption can happen anymore. So what the application here for GeoDict is, you can see, okay, how effective is my desorption process? And for example, how often can I cycle adsorption and desorption at different stages? And now to the conclusion. We can use adsorption to get more insights on mechanical process of the filter. We save material, time, and the effort to design and test filter prototypes. This gives us the ability to shorten development cycles, even by using cloud capabilities, where we can either set up parametric simulations on a very large scale, all finishing at the same time. And what I think is one of the key parts is to understand the product by simulative insights to see where adsorption can be improved, how can we give more time and optimize the flow at adsorption in our application. A small outlook, we'll come to that also later on when we look at the roadmap. So far, the adsorption has not been validated. We will look out if there are possibilities to do that. The equations we are now using are now only focusing on gases. We'll also extend them for liquids to use them also in, for example, water treatment. Temperature changes during the process. We know that there is, when we have adsorption taking place, that most of it is an exothermal process, and therefore temperatures locally may change. So this is also something we are having on our roadmap. And on a very, how to say, longer terms, we have also a presentation tomorrow, which deals with part of that, is that we have an entirely new solver, which is not Lagrangian Euler-based anymore, using tracers as we're using now, but we can use here an Euler-Euler approach, which then moves concentration fields through the domain. This is a lot more efficient, and we can also use in high concentration fields. But I think to have both options available in GeoDict is very nice when we move to very low concentration applications like semiconductors, microchips, and when we have large concentrations, we can choose a different solver, which is more efficient and cover both applications. Yeah, then thank you from my point, and I will hand over to Jonas to give a live demonstration on the structure generation for adsorption and adsorption simulations. Thank you.
Okay, then hello also from my side. So I just have one slide to showcase what I'm going to show you in the next few minutes. So the first part will be showing the structure generators of GeoDict, how you can basically create a digital twin of your material using the structure generators on these two examples that you've already seen before. And then in the end, how you can set up a adsorption simulation and what the results are. This part will not be live. It will take a little bit too long, but the rest will be live. And so for the first part, we will create this combined media. And this consists of these three layers that we've seen before, two fibrous layers and one activated carbon layer. So I will start by creating the first fiber layer, and I will use FiberGeo and create fibers for that. I first rename this. This will be our bottom fiber layer in the end, so I will just rename this to this. And keep the settings as is, create a little bit larger in Z direction because we want this stack. We don't want any fiber overlap because it's quite unrealistic if we look at a real sample. In this layer, we want quite a low volume percentage. And in the fiber options, I just removed the default ones. Here we use some curved circular fibers. And we use two different types. And now we want to set the volume percentage of each of those, and we just want 50-50. I can change this here. And then we can set the diameters. In this case, we choose a Gaussian function for the distribution of the diameter of these fibers. And this mean value here is 4.5, and then we just have a distribution around that we can see here. The length we will increase to double the size in X and Y direction because we don't want too many fiber ends in our structure in the end. And the orientation should be anisotropic, which is already is by default, but we still increase the anisotropy a little bit more. And you can see it favors the X direction and mostly in the XY plane. For the second fiber type, we will do a very similar thing, but we increase the mean size of the fibers here. And we also choose the same parameters here. Don't change this. And we will increase the anisotropy a little bit. So now with these settings, we can already generate our structure, which will only take a few seconds in this case, because the longest part here is to remove the overlap. And because the solid volume percentage we have here is quite low, this will be very fast. We have the debug output. Don't need that. So here we can see the voxels that are overlapping, and they will be currently removed by moving these fibers around. But here it's quite easy to find the ideal structure without any overlap. And when this is finished, we can continue. It's finished now. Get a result file, which we don't need right now. And then we can have a look at the structure at 3D. Visualize this a little bit more nicely. And we have these two fiber types in our structure. Now for the final sample, I want these fibers to be the same material. So I will reassign this, and I will reassign material ID and change all of the fibers to one material ID that we have then in the end. So the next stage is to create these activated carbon grains. And these we want to pile into our structure. And for us to be able to do this, we need some empty space. So we also use process geo, and then we embed our current structure. And we will add some empty voxels in Z- directions because we are piling the grains from the Z- direction. And we also add a little bit of voxels because this will be our inlet if we run later on any flow simulation. So we can just add and we create some empty space. And now I will just flip this. So the grains that we are in the next step piling in are coming from this direction. So we do this, we go to grain geo, and we want to pile our grains into the structure. To be able to do this, we pile in our current domain, and we also want to keep the fibers that we have right now. We don't want any overlap, and we just want to fill it up completely in the objects. So now to create these activated carbon grains, what can be very useful are these convex polyhedrons. And here we can define quite complex polyhedric structures. So here we change the point mode, how these points are distributed to surface. And we also want to vary these corner points a little bit. So here we choose uniformly, and we want between 7 and 10 corner points. And not that many. And then you can define an enclosing object. We can stick with the sphere here. And we also want a uniform distribution, and we go between 50 and 200 micrometers. Then we define the object motion, so how the piling is basically simulated. Because of the time constraints we have here, I will reduce these requirements a little bit. So this will not be the perfect piling result, but it will be quick enough. So with this, we can start to pile them. And this also depends on the geometry of the particles. So these are a little bit more complex than spheres, for example. So this takes a little bit longer, but it shouldn't take too long, I hope. So it should be 1.5 minutes roughly. And as a result, we will have these grains then piled on top of our fiber structure, but they will be quite artificial still because they have completely flat planes between those corner points that you will see. So I will show you a bit more functionalities afterwards, how you can make them a little bit more realistic. And I guess this time overview in this case calculates with I think the perfect piling. So this is not correct in this case. It will be quite a large jump after, I think it's 7 or 8%. So in this case, we just wait a few seconds. So on my laptop, it took 1.5 minutes roughly. Should be the same here, I think. Yeah, I think it's fine. It's 7-8%, and then it will jump. In a later stage, we also have a piling of spheres that will be much quicker. So now we have the grains that we have piled on top. And as you can see, they are not really looking like anything you would expect. So the first thing that we can do is we can roughen the surface to get some variation here. And here we, of course, we want to roughen our grains, which are solid number 2. Then we can define a feature radius, which we set to 25 here, and the distance, how we want to vary it. And then we vary the surface by adding and subtracting voxel. And we also want to check for connectivity, so we don't have anything freely lying around later on. And this will now go over all the grain surfaces and modify them a little bit. And then in the next step, we also want to add some, so as Philipp said before, these particles have porosity that is not resolved that we are simulating in the end. But for these particles, we also want to add some resolved porosity in addition. So we have pathways that we will simulate later on with the flow, or we can simulate. In this case, we don't use the structure for the simulation. I will show you how you can add some basically random porosity to these particles in the next step when this is finished here. And in the end, yeah, of course, we need to add the second fiber layer as a final step. It takes a little bit longer than it did before. But yeah, now this is finished. And now, as we can see, we have some rough surfaces on these grains. And to add the porosity, I first need to save the structure. So we can just include what we have in here. And we can get rid of it. And to generate some random porosity, we will use a Gaussian random field. And this here, we need to set the same domain size as our structure had before, which is after the embedding this size. And then we can define here a Gauss function in all spatial directions. And I will just change the standard deviation to 2. And run this. And now we get a volume field that has random distribution of values depending on the Gaussian field that we have defined. And by using a threshold, we can then separate between pores and solid voxels. And these solid voxels we can then subtract from our other structure to create some porosity. And by basically tuning the threshold value, we can tune the porosity that we want to add. So now we have this volume field with the same dimensions. And if we right-click the volume field, we can threshold the structure. And if we select 0, the Gaussian distribution is around the value of 0, so it will be 50% porosity. If we want a little bit less porosity, in the end, I choose 0. Oh no, I then 0.5. And then run this. And now we have, if I disable the volume field, you can see the structure. 30% is solid, and we will subtract the solid voxels in the next step, so it will be adding around 30% porosity. What I also want to do for the structure now is, before I save it, I want to change the material ID. So at the moment it's material ID 1 for the solid. I want to change it to material ID 2, and I will explain to you why in the next step. So now we also save the structure. Gaussian random field. We load our old structure. And now we can use layer geo to subtract the random field from it, but we don't want to subtract anything from our fibers. So that's why I changed the material ID. Now, if I click subtract bitwise, it will only subtract from the material ID 2 because it has the same material ID. So now the fibers are still intact and we have some resolved porosity in these activated carbon grains. So we save the structure as well. Use the name and add porous in front of it. And in the final stage, we of course use fiber geo again to create the second fiber layer. And here we create a new structure for now, which only has 100 micrometers, but it has a higher solid volume percentage, 15%, I think. And Here we use completely straight fibers, so we can use infinite fibers with the circular cross-section, so we won't have any fiber ends in our structure. And we can also use a set diameter and also add some anisotropy, so we have an XY plane orientation. So this will now take a little bit longer than the previous fiber generation because we have much more overlap, as you can see here. And this is a bit more difficult to remove. And at some stage, we will also, because we allow it by default, start to deform the fibers a little bit. And this will reduce the overlap voxels quite strongly. Settings correctly. And then in the next step, we have basically created now a new structure that we can attach to our old structure. And then we have these 3 layers together that we could then, for example, use for an absorption simulation. Yeah, now it starts to deform, which takes a little bit longer to compute, but it will reduce the overlap voxels quite drastically. 9, and then be finished afterwards, yeah. And then we have this fiber layer that we can again save, for example, as top fibers. And just to be able to separate it, I will again reassign the material ID of this one. And this will be now our material 3. And then I should save it again. Should have done before saving. And now we load the old structure. Porous particles. And we can use, again, layer geo. And in this case, we use attach. And we want to attach them from Z- direction. So we have to select this. It's the correct structure. And then we run this. And now we have a few things that we need to post-process. The first thing that we can use, for example, is also in process geo, we can compress our structure a little bit in Z direction. So here the default, we need to compress. And the default is 10%. We can just use this to press our structure a little bit further together. And then another thing that we also should take care of, because we added this porosity just by subtracting voxels, we are not sure if everything is still connected. We can also use the cleanse function, which just removes components that are smaller than these voxel numbers. This is usually much easier than for the flow simulation, for example. If you have single voxels flying around, that's not very helpful. And the last step that we need to do is the adsorption simulation always runs from Z- to Z+. And if we want our flow to come first through this fiber layer and then come from the bottom, we can mirror our structure Z-axis. And then we would have our final structure. Now we can turn it around, and this would be the final product. Okay, then we continue with the packed reactor. So this will be a little bit quicker. So first, let me just get rid of all of this. And then to create a container, we will use a GIC module. And so first of all, we can set our domain size, and in the end, we want to end up with a tube. So we also increase the Z direction again. And we also increase the voxel length in this case to 10. And now in this domain that we create, we just want to add one fiber. And here we can define the endpoints of this fiber. So it should be in the center of our domain in X and Y direction. And one endpoint should be with a 0, and then the other one should be, in this case, 9,000, so 900 voxels times 10 micrometers. And the diameter is 2,900 because we want some rim around the structure in the end. So if we click run, this will be very quick. We will just end up with this fiber. Now, if we right-click the structure, we can invert, and this will give us a tube. And now we can again use grain geo to pile the grains. And I want to first get rid of all the settings that I did before. And then we pile in the current domain and keep the current structure, of course. Don't want any overlap, we fill it completely. And here we just want a sphere. And the diameter we also vary. Spheres of different sizes, between 500 and 700 micrometers. The object motion, I guess we can leave as is. You can see it should be not too complicated. Now, I didn't name the previous file. In this case, I can just overwrite, but depends on what you need. And now the piling of the spheres should be much faster than the polyhedron. And for this case, we also have a tutorial available on the website where we use more complex palette shapes. So you can also design palette shapes with, I think in the example are some holes inside of the palettes as well. So you can design them and also pile those grains. So yeah, whatever design you need.
We have in our integrated test system for this, we have a test where we pile small Christmas trees. So yeah, it even works with very complicated geometry.
Yeah. And then we just end up with this kind of structure. And now if we are happy, we can just use this for an adsorption simulation, for example. And on an example like this, I will show you how you can set it up and then what the results are like. So to access it, we go to predict and then we go to Addidict. And then down here, we go to the Advection Diffusion GeoApps and choose adsorption. And if we click edit, we get some settings. I cannot show all of them, so I will scroll through. I will load some settings that I've used for the simulation that I will show you the result file of later. And I've saved it to a newer GeoDict version, so that's settings, but the settings are still the same. So up here you can, is in every dialog given result file name, then you can set the total duration of the simulated time that you want to simulate, the number of batches, as we have heard before. The tracer per inflow voxel is basically how precise you simulate the distribution of the adsorbent in the system. The default value is 5. You should not go lower than that. Otherwise, you can get artifacts. You can increase it further, but that, of course, increases simulation time. So then here you could start, if you want to do a desorption simulation, you could select you want to start with an already adsorbed state. So you can load this. This will be one of the results later on for the adsorption simulation. So you could load one of the results here to desorb again. The processes, of course, for the parallelization. Then here you can set the simulation parameters for the flow-dict simulation. And then down here, scroll now, you can set the parameters for the adsorption, so the concentration, then the two diffusivities in the pore space and inside of the adsorbent material, the temperature and pressure. And here then you need to define which material ID is adsorbing. You can set the permeability, density, porosity of the particles, the mass transfer coefficient. And down here you can now select the Toth and the Langmuir isotherm models, and depending on what you choose, you need different parameters that you can get from literature experiments. You can also get a table if you have some values yourself inside of the table that you can import. And once you have set it, you can just click OK and run it. And in the end, when you have finished, you will get a file like this. Of course, again, a GeoDict result file. you see how many batches were solved. You always have an initial batch, so that's why it's 21. And then you can calculate, you get calculated different times at what 5% of your inlet concentration reached the outlet. So it's 1.5 hours, then 50% is after 2.1 hours, and the saturation is after 2.7 hours. You also get this in a table, but you can get it a little bit nicer in a plot. So the first plot we see is the isotherm. Then we can see the average load per layer for all the batches that we have computed. So you can see the progression throughout your structure for the adsorption. So which layer becomes saturated at what time. The breakthrough curve, so the outflow concentration over time, and also the adsorbed amount over time. It's to see which time you get saturation. To visualize it, you have down here, first of all, the flow field and the trajectories, but for each batch you have separately the adsorption state. So, for example, load one of these, and we go to the main window, we disable the structure, and we only want to see it, of course, on the particles. You can see now this is the direction. Here you see the load on the particles and the distribution over this structure. So, and using all these information, you can also create a video for reporting. You have we have a macro for that available. You can add 2 plots, the breakthrough plots and the layered adsorption. And I have also generated this. So here you see the 2 plots, and they also basically add their points over time. And in the center, you see the distribution of adsorption. But you also see by using both of these, so here you would think that the adsorption, the saturation state is reached a little bit earlier, but as you can see in the breakthrough curve, there's still some adsorption happening inside that you don't see with the visualization that I've chosen for this video. But you can choose different kind of, you can also cut your particles, for example, if you want to look what's happening inside, what we've seen before for the adsorption. In here, clip Y. You can see the state that's happening inside of these particles. And yeah, with this, thank you for your attention. And if you have any more questions for the second part, we have a little bit of time, I guess.
Hello, everyone. We will now continue with our session. Next part is a live demonstration of how to import and actually changing structures of a complete filter. So this is what we're gonna do. So first we're gonna import a CAD data from a structural filter. Then we will actually change the pleats in there. We will add them to the filter and then prepare the complete filtration simulation and actually see how the flow behaves through the structure. For this, I've also prepared some small calculation sheet, which we will use to actually calculate some diameters. Those values normally you can easily obtain from your CAD data or from your CAD engineer. If you do not have them in there, it's really straightforward how to actually change them and how to actually calculate them. We will start the process now. So like I said before, the first part is actually to import the CAD data. For that, we will import our structure. In there, the first thing you should always do is like to check if the unit in your file is the same as in the import cut file. In this case, it will be meters. And we then have to definitely check like what are the lengths in here and what are the dimensions in there. For that, we have an option to actually suggest those in GeoDict. So if you choose the voxel length, for example, then the voxel length of the structure generated will be 300 micron, and GeoDict will definitely then calculate all the other values in there. One also very important thing is that you should always check what the pore material looks like. In this case, we have an oil filter, so we change the pore material to oil. After that, we check these values, and they pretty much see that the voxel length is fine in there. And after that, we import the structure directly in GeoDict. This will take a few seconds, and after that, we will have the structure then in GeoDict, where we can actually then change the pleats inside of GeoDict. So we do not need the surface triangulation now, so I will just skip that. And as you can see here, this is like the structure we have imported into GeoDict. And from this point on, we can actually also slice through the structure and see how the structure looks like. And if you slice through the structure, pretty much you can see that we are having a filter in here, and we want to get rid of this filter because we want to actually change the filter with another filter. So like I said before, to actually change the filter, we need some dimensions of the filter because the new filter should fit in the space where the old filter was. And for that, the easiest way is actually to go to 2D view and change the right angle. I will just unclip the structure. And from this point on, we can pretty much go through the structure. And as you can see, at some specific points there, we will actually see that the filter starts, the pleats are actually in there, and you can directly see them. So because we want to know the total length of the filter, the easiest way to see that is that we actually slice with the filter and see that on slice 32, you can first time see the pleats in there. So like I said before, we are having a calculation table, which is straightforward, which says like the pleats start position was 32, and then we slice through the structure till we get to the end of the filter. And as you can see here, the last slice is 315. So what we basically do is we write in the last slice in here, and this sheet, what it does is pretty much it calculates the total length of the filter, which is like the end position minus the start position plus 1. This is the length in voxels, and this is the length in millimeter afterwards. And you can normally easily obtain those values, like I said, from your CAD engineer, or you can also obtain these values directly in GeoDict. So the next thing to actually model a filter with the same dimensions, we have to know also the dimension of the outer and the inner diameter. So the easiest way to actually obtain these is also to clip through the structure. And as you can see here, we can clip in X direction. And at one specific point, we will then see if we go one slice deeper, we will get some looser information of that and actually cut one tip of the pleats. So we pretty much know that the outer diameter of the pleats starts at 12. So it starts at 12, and we go to the other side to actually see what's the end position. And as you can see in here, the last position is 239. So we type in that value in here, and it definitely also then will calculate us the total amount of voxels and the total amount of in millimeter directly. So what we also need after that is we actually need the inner diameter, because we want to have a circular pleats afterwards. So we do pretty much the same thing. We will also measure the inner diameter. So we slice again, and we will see that the last part in here is 53 actually. So we go back to the sheet and type in here 53. And do the same thing from the other side. So the last slice is 198. So we have all the values we actually need to replicate a pleat who has the same outer inner dimensions. So we actually can then from this point on switch the amount of how many pleats it should be in there, but the outer and the inner dimension, the length should be the same of the filter now. So the first thing we have to do afterwards from that side is we want to get rid of this filter inside of that because we want to replace it with a new filter. So the easiest way to actually get rid of this is you have to look for the filter media. In this case, it was ID number 5. You could also slice through the structure again to see like if it's the right media. And as you can see here, it's also written in there. It's voxel material number 5. So we want to reassign the material of ID number 5 to our fluid, which is in this case oil. So what you're going to do for that is we assign material IDs. We want to reassign ID number 5 to our new ID number 0, which is oil. And if you run this, you can pretty much see that the pleats are gone in this complete filter now. From this point on, we actually want to save the structure because we will, as a next step, create a new filter which has a different amount of pleats with the same dimensions, and we will then add this filter inside of GeoDict. So what you're going to do now is we will actually save this structure, and we will save this structure as filter without pleats. So the next step is after that to actually create a new pleat, pleats in there. For that, we go to Pleat Geo, and we want to have a cylindrical pleat in here. And from this point on, we have to actually check. The first thing we have to check definitely is that the voxel length of our new pleat has actually the same voxel length as the complete filter, because otherwise we cannot add them to each other. So we check that the voxel length is pretty much the same, which is 300 micrometer, which here says 0.3 millimeter, which is the same. And from this point on, we can then change here, for example, the number of pleats in here. We can increase them, we can decrease them, and so on and so forth. And in this regard, let's go just for 50. You could also use an M pleat pattern in there. You could also use different shapes. But the first thing it actually asks you is like giving the inner diameter and the outer diameter. And that's why we have this sheet in here, and which says like the outer diameter is 68.4 and the inner diameter is 43.8. And I've also already added those values in there before, so that this actually matches the size of the filter beforehand. We could model the complete height in there, but there's a faster way in GeoDict, because otherwise it will create a gut object, which is incredibly powerful, but it's not needed in this regard. And this gut object takes more time to generate. But in this regard, we just go for a very small height, and then we will increase the height of the filter completely. You could, in this regard, you could also add more layers. You could also change the thickness of the layers in here. But for this showcase, we just leave it as it is now, and then we pretty much generate a new pleat in here. And as you can see here, it is currently a very small pleat in here, but you want to enlarge it to actually fit in our new filter in there. So we want to repeat our structure, and our structure is currently 7 voxels large, and our structure should be in total 284 voxels in here. As you can see here, those are the values we obtained at the beginning. So which means that we have to increase our structure by 277 voxels. We will run it, and then we have the new complete pleats in here. The next thing we actually want to do is we want to change the material ID of our material 1 because we later want to add it to the old structure. And if we keep the material ID 0, 1, and the other one is also 0, 1 in there, they are not distinguishable after all. So we will change the ID firstly. So for that, we just go for structure, reassign material. We want to reassign material ID. And last time we used ID number 5. That's why we can also use ID number 5 now. And we will run it. So then it will be ID number 5 in here. From this point on, we just save the structure. We save the structure as it's in here. And we will actually load our GDR file. We will use load our filter without pleats beforehand in here. And from this point on, we will use layer geo to actually get those structures together. We just add a new file in there. And for that, we want to add the pleats in here. And because you can see those dimensions do not match perfectly because this is has a larger X and Y direction. And we want to make sure that we have it perfectly placed in there. So we need an offset. And the offset is like the difference between those two values, the half of it. So it's like 12 in X direction, 12 in Y direction. And that's why we just looked at the start position of the pleat. It started at 32, so our offset should be 31 in that direction. If you do this, we can load this, and as you can see now, when we slice through the structure, oh, sorry, this was the wrong one. You pretty much can see that we are currently now having a new pleat structure in here, which you can also see in 2D slice. So the one thing you should always check is is the pleat at the right position? So is it in the center, and does it actually start also at slice number 32 as the one before? And this is for this case, this is for this structure the case, and you can slice them through the structure and see that it also ends at the same position, which means that we pretty much gave them the right dimensions to fit in the structure again. From this point on, we can then definitely start to set up a flow simulation. So to actually start a flow simulation, we need to clarify some things, which means that we have to check first what is our inflow, what is our outflow, and we, as you can see here, the last slice here is empty. And we do not want to have the last slice empty because if we flood fill our components later on, they will also flood fill inside of the filter. So we want to get rid of this last slice in here. So what you're going to do for that is we pretty much crop out the last slice. And then you can see the last slice is now our last slice of the complete filter in there. The next thing we want to do to actually start a simulation, we need to define the inlet and the outlets. For that, we select all the inlet parts. And we want to fill only the component plane because we want to only have this as an, not the complete component, but only the component plane, which is like one slice as the inlet. So we need to define a new material ID, which is not used in here yet, which is then ID number 12. And so we do not get confused laterwards, we also set in some material information which are just like disregard inflow. We will click run, and as you can see now, those parts are now defined as the inflow. We will then, later on, we will select this one, use a new material ID. We will set this as outflow. We will run that. And we want to be sure that everything else, which is not inflow or outflow or inside of the filter, is solid, so that the simulation runs perfectly. So we pretty much select a voxel in here, let's select a voxel in here, and we want to run it as a flat fill component, which means it fills up the whole space as a new material. In this regard, we use anterior ID number 14, and we just call it outer solid, so we do not get confused. This will take a few seconds, and as you can see now, our structure is now completely, the outer things are solid. These are named as inflow, these are named as outflow, and as you can see through the structure, oops, the inner part is not touched at all, which is disregard awesome. So the next thing we should do now is we have to check all the materials which are written in here. Because as you can see here, the ID number 14 is oil, which should be outer solid, but oil is not solid, so we have to change the material of the ID number 14 to an actual solid material. And yeah, that's what we have to check the next thing. So for that, we go to Process Geo. We will reassign the material of a material ID. And this is, we will change from ID number 14. We will change it to a new material. And in this regard, it should be solid. And we also give it a name tag so we do not get confused afterwards. So in this regard, we will reassign it. And as you can see here, number 14 is now solid. Inflow and outflow should be oil because it's an oil filter in this regard. And we also have to check if the material of our actual filter is a porous material, because if it's not porous, we cannot set up a flow simulation. If this is the case, which is the case currently, it's oil and porous, the next thing we will actually do is we will set up a flow simulation, and we want to simulate a flow experiment for the complete filter. If you open this, you pretty much get all the information in here, and you can see on the materials again, and you could definitely also reassign them in here. What is very important is that everything whenever there's fluid in there, it has to be the same fluid everywhere, and then you have the green check marks, which is the case in here. And after that, you have to also give the porous material also definitely permeability, because otherwise we cannot have a flow through the structure. In this case, we could use E1 minus 10, for example, and then you can also, then the next thing you have to do is pretty much say what is the inflow and what is the outflow of the structure. This GeoDict directly pretty much gets from the names, you name the structures in there, what should be inflow and outflow, but you could change it. In this regard, GeoDict realizes that we named it inflow, and it takes number 12 as an inflow, and it takes number 13 as an outflow, because we named it that way, but we could actually also change it in here. We can, from this regard, we can also then set different boundary conditions like an pressure, or we could also say, like, we want to have a different flow rate at the beginning. So we could, for example, go for 4 liters per minute, for example, and then run the simulation. This simulation will take a few minutes to actually compute, and I will not start it yet, but I will definitely load the result files so you can see what you can obtain from these results. So then I will load the structure in here. So you can see that our flow rate was 0.03 liter per second, and the result is that our pressure is 240 pascals. You can also then visualize the whole thing. I will first load the structure, so we are clear, and as you can see, we are pretty much having the same structure. I just use the same structure as simulation, and then you can also use the flow visualization. Just load them, and from that point on, you can we want to see every material in here. And as you can see here, we can now get rid of the structure and see the flow fields through the structure. And we can also, for example, you can slide through these areas in here, so you can pretty much see what happens inside of the filter, how's the velocity through the filter, and so on and so forth. And the good thing is also you could also look for errors through the structure. And I will just get rid of that, and I will increase the error scale for 2000. Oh, this is like too much. 500. And we'll slice this X direction in here, and you can pretty much see how the flow behaves through the structure and where the flow goes. And you can also mark them as the velocity, depending on the velocity, so you can pretty much see where are the faster areas of the flow through the structure and where are the slower ones. And this is basically how you set up a flow simulation in GeoDict, and also changing the pleat inside of the structure. You could always, for example, use different amount of pleats, also different pleat heights and pleat shapes in GeoDict directly. And as you can see here, just to set things in perspective, the runtime of this specific structure was 19 minutes to complete the flow through this complete filter in here. I'm open for your questions now, and I hope I made it clear how to set up a flow simulation in GeoDict.
So then I will shortly jump to conclusions and outlook, and then we'll move on to the roadmap to finish on time and get some coffee. So yeah, we showed, I think, a bit of the latest and greatest features. Here highlighted from media scale to the filter scale. We showed that we have significant improvements on the media scale. Nowadays focusing quite heavily on air filtration. So topics like adsorption, electrostatics. But we also plan to do improvements on the basic filtration, like for example, collision models. We'll come to that on the roadmap. Then we have always a challenge, as we can simulate on media and on filter scale, that we need to bridge somehow the gap between these kind of multi-scale approaches to still be efficient. For this, we constantly try out new approaches and improvements for this multi-scale simulation. So how can we effectively describe the media in an element or a complete filter simulations without resolving each fiber individually? So one of the parameters, for example, is permeabilities, porosities, and for filtration, we have also some parameters. But to make this very user-friendly and efficient, we constantly try to involve these features in GeoDict. Furthermore, as you saw, we have a continuous improvement in Pleat Geo and the handling of CAD structures. This means we implemented just cylindrical pleats last year. Then we also extended or enhanced this by the M-pleat shape. Quite recently, I think it was last week, we had that we have not a constant change in the pleats, but they can be of individual height. So they can be not on a pattern, but we set them as different heights individually. Then working more on the elemental scale or filter scale, we reach out in the regimes of turbulent flows, where we have high flow rates and air, which is dedicated for turbulent flows. One addition we have here is the subvoxel resolution, which is one technical step in the direction towards the simulation of turbulent flow, which will be part of the implementation in the next years. This brings us also to the actual roadmap for the filtration with the rough plannings for GeoDict 26 and 27. For 26, I think we were to further improve the subvoxel resolution, dedicated also for filtration. So this is one now part of GeoDict 2025, but still needs to undergo improvements, which then leads to hopefully the simulation of turbulent flows. By now, the techniques which of interest would be LES, like Adtendees simulations, as we have here very few parameters which we give guys on hand. So there are also other models, like I think well-known Reynolds average Navier-Stokes, but they are quite complex and have to deal with a lot of parameters, which you need to know actually. Then, as already mentioned, multi-scale simulations. So how can we go from the media to the complete filter, or like to filter element simulations, where we work in the unresolved scheme to still reproduce the media results, or the results which we obtain by experiments. Complete filter in its entire range is constantly a topic. So this means increasing the user friendliness, increasing the runtimes, performances, increasing the features which we are given, either might be pleats or might be to work around with CADs. So one thing we are having on the commits to check the mesh, so at least give feedback on the quality of the CAD input, so that the simulation is also successful, and to give the tools to fix certain problems. Then, as highlighted here in gray, we have the topic of air filtration, which is one of the features we are focusing on. This starts with the implementation and testing and validation of the desorption, the adsorption for liquids, which then leads also in 2 or 3 years to the adsorption solver, which is then Euler-Euler based. Electrostatic decay, we still need to validate with experiments. We have some functionality inside, but I think this is still under improvement. And one thing which is now on the agenda for 2026 is the improvement of collision models. So here we check different collision models. By now we have the Hammaker and we have the cordon first touch and sieving, but either we add an additional one or we just improve one of the existing ones, taking into account the collision model, surface roughness, for example, or anything like that, improving the validation with experiments. One key driver, I think, which I don't see next year, but in the next years, would be like coalescence. So we have this feature in GeoDict due to a publicly funded project 2 years ago, but still we have no validation for an experimental case. This would be something we want to take care of either with a collaboration with one of you guys to see, okay, what do we need to add and how well do we perform to measurements. By now we still reproduced only theoretical values. And then a very long topic, I would say, and I think the time frame is not 100% sure yet, is we want to go from 2D analysis to 3D digital twins. I think in the morning you saw that this is already implemented for the granular media, but for fibrous media this is a bit more challenging, as we have highly anisotropic features here. I think the benefits for 2D analysis, they're cheap. Everyone has them. They don't have restrictions on resolution like microstructure, for example, has. But on the downside, you lose information as you don't only have a 2-dimensional representation, and you lack of the 3-dimension. So ideas here would be to start with simple analysis of 2D. So you load SEM, you get fiber size distribution, you get porosity, something around that. And then maybe ideas circle around to have like several SEMs from different directions, and to set that together to 3-dimensional digital twin, which allows them for optimization using Python scripting. On the very right-hand side, we have topics called later. So these are things which are on the agenda, but not dedicated to a specific year, which depend on the ideas we're having and the personal situation we are doing. So ideas here are bacterial growth, which we have been requested by several customers, as testing here for laboratories is quite expensive. And doing that simulative would be a huge benefit of that. Non-spherical particles, is always, I think, a challenge, but yeah, which adds another level of complexity as we now then deal also with rotation and this kind of stuff. Yeah, which I think is not from the technical side a huge implementation, but performance-wise. Import cut improvements here allow several formats. By now we have OBJ and STL, but a lot of customers use step still, which is a little bit older, but yeah, to get here some more usage in this regard. Crossflow and membrane technologies go hand in hand. So we had some projects with membrane technologies. So and a lot of membranes we move to different regimes, like Perclay regimes, and which differ from the Stokes regime, especially when we go for ultra and ultra fine filtration membranes. So this might be also a topic in the future. And then I will thank for your attention. We are now starting discussions, and thank again for Jonas and Christopher for the live demonstration. Thank you.